Have you ever wondered why things fall, how objects move, or why the sun shines? Welcome to the fascinating world of physics. In just 10 minutes, we'll simplify the basics of traditional physics, the science that explains the physical world around us. From the smallest atom to the largest galaxy, physics governs it all. Join me now as we unravel these threads and begin to comprehend the elegant laws that dictate the behavior of the universe. What exactly physics? It's a question that has captivated the minds of thinkers for millennia. In essence, physics is the science of matter, energy, and how they interact. Imagine a child at play with a set of building blocks, each block a fundamental particle, each combination a new and complex structure. Physics seeks to understand the rules by which these blocks interact, the forces that hold them together, and the energy that drives their motion. From the smallest subatomic particle to the largest galaxy, physics seeks to explain the world around us in its entirety. The way a ball bounces, the reason a car moves, the warmth of the sun on our skin, all of these phenomena can be explained by the principles of physics. At its core, physics is about asking questions and seeking answers. So, as we delve deeper into the world of physics, remember that we are embarking on a journey of discovery, a quest to understand the fundamental nature of our universe. In the heart of physics lies the study of motion, a field we call mechanics. Here we encounter the groundbreaking work of Sir Isaac Newton, a scientist who forever altered our understanding of the universe. Newton's 3 laws of motion provide the foundation for understanding how objects move and interact. His first law, the law of inertia, states that an object at rest will remain at rest and an object in motion will continue in motion unless acted upon by an external force. Picture a ball rolling across a table. It would continue rolling forever if not for friction and air resistance. The second law quantifies the relationship between force, mass, and acceleration. It states that the acceleration of an object is directly proportional to the net force acting upon it and inversely proportional to its mass. Newton's third law states that for every action, there is an equal and opposite reaction. When you jump, you exert a force on the ground, and the ground exerts an equal and opposite force on you. But what about the force that keeps us grounded, the force that governs the motion of planets and stars? That is the relentless pull of gravity. Gravity is the force of attraction between any 2 objects with mass. It is a fundamental force of nature, shaping the universe on scales both large and small. Energy, the very essence of motion and change, is a concept as fundamental to physics as time and space. It is the driving force behind every process in the universe, from the smallest atomic interactions to the grand movements of celestial bodies. Energy exists in many forms, but 2 of the most fundamental are potential energy and kinetic energy. Potential energy is stored energy, energy poised to be unleashed. Imagine a coiled spring ready to spring back to its original form, or a rock perched precariously on a cliff edge, ready to plummet. Kinetic energy, on the other hand, is the energy of motion. The faster an object moves, the greater its kinetic energy. Think of a speeding train, a soaring bird, or a rushing river. Energy can transform from one form to another, but it can never be created or destroyed. This is the fundamental principle of the conservation of energy. Consider a roller coaster as it climbs a steep incline, its kinetic energy transforming into potential energy. As it plunges down the other side, this potential energy is converted back into kinetic energy. The lights we use to illuminate our homes, the cars we drive, the computers we use to communicate, all of these rely on the principles of energy transformation. Energy, restless and ever-seeking, often finds its voice through the language of waves. Waves are disturbances that carry energy without carrying matter. Imagine a pebble dropped into a still pond. The ripples that spread outwards carry the energy of the impact, yet the water itself doesn't travel with the waves. Sound, the very essence of music and communication, travels as waves through the air. When we speak, our vocal cords vibrate, creating pressure waves that travel through the air to reach our ears. Light, the very essence of sight, also travels as waves. But these are not waves of matter, but waves of electromagnetic energy. These waves travel at an astonishing speed, allowing us to see the world around us in all its vibrant detail. From the gentle lapping of waves on a beach to the roar of a thunderclap, waves are everywhere, carrying energy across vast distances and shaping the world around us. Heat, a fundamental concept in physics, governs the transfer of thermal energy between objects. It's the driving force behind countless natural phenomena, from the melting of glaciers to the eruption of volcanoes. Temperature, on the other hand, is a measure of the average kinetic energy of the particles within an object. The hotter an object, the faster its particles move and the higher its temperature. Heat always flows from hotter objects to colder objects. This is why a cup of hot tea cools down over time and why ice melts in your hand. The thermal energy from the hotter object is transferred to the colder object until they reach thermal equilibrium. This transfer of heat can occur through three primary mechanisms: conduction, convection, and radiation. Conduction involves the transfer of heat through direct contact. When you touch a hot stove, the heat is conducted from the stove to your hand. Radiation, the final method of heat transfer, involves the emission of electromagnetic waves. This is how the sun warms the Earth, with electromagnetic radiation traveling through the vacuum of space to reach us. Traditional physics, the foundation upon which our modern understanding of the universe is built, may seem at times like a collection of abstract theories and equations. But in reality, it is the driving force behind countless technological marvels that shape our world. From the bridges that span vast rivers to the airplanes that soar through the sky, from the smartphones in our pockets to the power grids that illuminate our cities, traditional physics underpins it all. Engineers rely on the principles of mechanics to design structures that can withstand immense forces, ensuring the safety and stability of our buildings and bridges. The principles of thermodynamics are essential for the design of efficient engines and power plants. Our cars, trains and airplanes all rely on the combustion of fuels to generate the energy needed for movement, and the efficiency of these processes is governed by the laws of thermodynamics. Even the seemingly mundane act of turning on a light switch relies on the principles of electromagnetism, a branch of physics that describes the relationship between electricity and magnetism. Space exploration, one of humanity's greatest achievements, would be impossible without a deep understanding of the laws of motion, gravity, and rocket propulsion. Traditional physics, for all its explanatory power, is not without its limitations. As we delve deeper into the realms of the very small and the very fast, we encounter phenomena that challenge the very foundations of classical physics. Here, in the realm of atoms and subatomic particles, the deterministic laws of Newton give way to the probabilistic world of quantum mechanics. Quantum mechanics describes the behavior of matter and energy at the atomic and subatomic levels. In this strange and counterintuitive realm, particles can exist in multiple states at once, and the act of observation can influence the outcome of an experiment. At the other end of the spectrum, as we approach the speed of light, we encounter the mind-bending world of Einstein's theory of relativity. These modern theories, quantum mechanics and relativity, have revolutionized our understanding of the universe, revealing a reality far stranger and more wondrous than anything imagined by classical physics. Let's bring these concepts to life with a simple example. Imagine a ball perched at the top of a hill. At this moment, it possesses potential energy, stored energy due to its position relative to the ground. As the ball begins to roll down the hill, this potential energy is converted into kinetic energy, the energy of motion. The force of gravity, pulling the ball downwards, causes it to accelerate, increasing its speed and therefore its kinetic energy. As the ball rolls down the hill, it may encounter various surfaces, each with its own frictional properties. Friction, a force that opposes motion, converts some of the ball's kinetic energy into heat, slightly slowing it down. This continuous interplay between potential and kinetic energy, governed by the forces of gravity and friction, beautifully illustrates the fundamental principles of physics in action. It highlights the interconnectedness of motion, energy, and forces, and how these fundamental concepts govern the behavior of objects in our everyday world. Physics is the science of everyday life. It's everywhere, waiting for you to discover. From the smallest atom to the largest galaxy, physics governs it all. As we've seen, physics is not just a collection of abstract theories and equations, it's a way of understanding the world around us. Thanks for watching. Now go explore the world with a new perspective.